machine room, and it's like a zoo. There's so many different systems to see there. I've never seen such a selection. It's brilliant. So today I was going to start with a brief look at what you do if you've got a parallel code. So for some people, this isn't really something that they're going to necessarily do. But if you're really going to use a system like a Cray XK7 or a big GPU cluster, one GPU will not do the entire job for you. You do need to have multiple nodes working together on the problem. So porting, this is the wrong presentation even, porting to such an application, that's better. I mean, at the risk of giving the game away, a parallel code is just like a scalar code, but with data transfers. You don't ignore the scalar part of the code, and so what we've been talking about so far is scalar optimizations. So for a parallel code, you do go through the same exercise that you would do, that we did yesterday, looking at a scalar code and tuning the kernels. But the other thing you need to consider is how data moves between between the different nodes. And the added complication when you're dealing with a hybrid system that has GPUs is that the GPU isn't talking directly to the network, at least in this sort of, when you start thinking about things. The GPU talks to the CPU talks to the network. So you have to manage that you've got these two memory spaces, the CPU and the GPU, and you have to make sure that the memory, the data that you want to send is in the CPU memory in order to talk to the network. Now, there are some ways that you can get around this that are more advanced, and I'll talk about that a little bit later. But this talk is looking at the sort of extra things you need to consider. So I'm not going to talk particularly about tuning kernels or anything like that, because we've done all that. So what I'm going to talk about is, first of all, in a more conceptual level, what sort of things you're going to do, and how do you do those in OpenACC. And then there are different ways, different communication models that you can use. You could use MPI, you could use Fortran coarrays, but I'll say a little bit about these two examples at the end there. But most of what I say is actually quite common to both of these calculations. So the code I'm going to talk about, because it makes it's familiar with what we've done before, is this Himeno code, this Stencil code that we looked at yesterday, running scalar. There's a parallel version, and so I'm going to talk about the parallel version because obviously the structure of the program looks very similar. So you've already seen a little bit about this. I'm talking about a strong scaling benchmark. So this is where you take a particular global problem size and you're going to split it up over more and more nodes. The code itself, I'm going to mainly talk about the Fortran version. It's about 600 lines of Fortran. To port this to the accelerator, we used about 25, 30 directives. So that's more than we were using for the scalar code because there is the extra complication of all these data transfers. So what does the code look like? Well, it's very like what we saw before. There's an initMT that initialized the local matrices. It calls this Jacobi routine twice. The first time it was calling it just to calibrate what it did later on. And there was the second call where it actually did a performance estimate. But the new thing in there is that it also has to set up the processor grid because it decomposes this 3D problem into a 3D grid of processors and then splits the problem over those. So if you want to do this Stencil update, obviously each local problem is going to have to share halos with its neighbors in order to calculate the full problem. And it's going to have to do that at each iteration. So the difference is when you look at the iteration loop that we saw before in the Jacobi routine, there's the loop over iterations. Obviously, that's a serial loop. It's an iterative process. Then there was a stencil that was taking the data array and calculating the new array from that, a temporary array, and it was also calculating a residual. The local residual here, for whatever reason in the code, is called WGOSA. But then And then later on, you're going to copy that back into the original data array. But the additional steps that you have to do is the halo exchange. So when you've computed this stencil, you have to take the halos of this array and you have to exchange those with the neighbors. And when those have arrived, you have to unpack those halos from the receive buffers back into the data array, ready for the next iteration. And in the middle, you're also going to have to do some sort of synchronization step, and that synchronization step might be at the same time that in order to calculate this residual, you need to do a global combination of the local values and all reduce in MPI language to get the total residual. So the stencil looks the same. The only difference now is that these loop bounds here are the local problem size and not the global problem size. But otherwise, everything looks identical to what we were seeing yesterday. You know, you've got forward nearest neighbors, backward nearest neighbors, next to nearest neighbors, forward and backwards, and appropriate weight factors being combined. So that's the same. And you know, if you were doing an OpenACC port, you would optimize this in exactly the same way that we would have done for the scalar case. But knowing, of course, that these local problem sizes are going to vary as we change the decomposition of our problem. So when you do this as a sort of flow chart, what happens is the CPU comes down, it calculates the stencil, it packs the halos, it sends the halos over the network, it does an all reduce of the residual. There needs to be a network barrier to make sure that the messages that were sent have been received. So we know we've received the buffers now, so we copy the bulk of this array into the data array, and we unpack the halos, and then we do the next iteration. Now, of course, you know, should I do this here? I could do that up here. It could be done before the barrier if I wanted, or before here. There's some freedom in how you reorder these tasks, even on the CPU. And which is the best order? Well, depends on your hardware, it depends on the communication library and how much potential there is to get overlap. It depends on the details of the kernel and the local problem size, because sometimes this is a big operation and sometimes it's a small operation. On the GPU, well, when you first start porting it, you basically take this and you offload these boxes to the GPU. So you do the stencil on the GPU, and then you synchronize, then you pack halos. Because you've synchronized here, you know that work 2 is finished and it's ready to pack the halos out. And then you send those halos back to the host when they've been done. Then you need to synchronize to make sure they're on the host, and then you send them over the network. Now, because GPU, you can launch kernels asynchronously, then you may as well immediately start copying this bulk, launch this kernel, and while this kernel is working on the GPU, you can do the reduction across the network of this residual value and set your network barrier. And then you synchronize here to make sure that this has arrived. And then the halos have definitely got here now, so I send those to the GPU and I unpack them. And at that point, I synchronize again because I know I'm ready now to start the next iteration. So we're getting a little bit of overlap here between CPU and GPU, but there isn't much scope there for overlapping things. And that's just with a simple OpenACC port. So by simple, I mean I'm not talking about using the async clause. I'm just kind of saying, what can I do if I just use kernel's parallel loop? And of course, I've got a data region there. If you have this async handle that I talked about, the ability to sort of launch streams of tasks to the GPU and know that they will be completed one after the other and only synchronize later on. Well, what you can do then is the first thing you've got to do is do this stencil, because that's giving you this array, which is going to be the basis of everything else. So you have to do that, and you have to make sure that job is finished. Then you've got to pack halos from here. Well, it's a three-dimensional code, so when I say pack halos, I've actually got to pack 6 halo buffers. X up and down, Y up and down, Z up and down. And I can do those in parallel. So in fact, I can launch 3 separate streams of tasks to do X halos, Y halos, Z halos. I could even do 6 separate streams of tasks. One stream's going to pack the X up buffer and then send it to the CPU. Another's going to do the X down buffer. Which is best here? Well, the answer is that's a tuning option as to whether you do it as 3 streams, 1 for each direction, or 6 streams, 1 for each direction and 1 for up and 1 for down. But you can overlap those 3 tasks together. And this will help, because you can only do one thing across the PCI bus back to the host at once. It will mean that jobs are queuing up and can use it as quickly as it's ready. So this does give you a speed up. Of course, you need these buffers to be ready and synchronized before you send them. But at this point, maybe even before that, you might even be able to start this even earlier. You can start copying the bulk, the internal bit that's not affected by the halos. You can start copying the bulk of P, the bulk of this temporary array into P, almost immediately. You could have started this even earlier if you wanted. You've still got to do the reduce, you still have a network barrier, but then you've got 3 or 6 receive buffers to send and unpack. So you've got 6 receive buffers. You can either do this as 3 or 6 separate parallel tasks on the GPU. Again, you have to make sure everything is synchronized before you start the next iteration. So you're getting more scope for overlapping things. I mean, these copies are very simple kernels, so it's hard to overlap something that doesn't take much time with anything. But this is where the potential is. For a different code, these may be more complicated tasks where the kernels take more time and there's more potential for overlapping. So at this stage, I haven't talked about MPI, I haven't talked about co-arrays. This is just a conceptual task-based view of your application. And it's very important to try and get that, to understand where you can find the potential to overlap asynchronous GPU work, asynchronous network communication, if you're using, say, MPI, iSend. So what would this look like if you really wanted to look at this? Well, here's an example of packing the X buffers. So what I would do is I would say parallel loop that's going to pack the X buffers. I'm going to use one loop to do both buffers. Should I use 2 loops? One for the up buffer, one for the down buffer? I could do, but it seems to be faster for this particular example to do it as one kernel. And I pack these buffers. I launch this asynchronously with an integer handle. That could be number 1, whatever. I then, as soon as I've launched that, I then say, I'm going to send these to the host with the same handle. So again, this is done asynchronously, but I know that this won't happen until that's finished. I do the same for these 3, for Y and for Z, so I repeat these, a kernel to pack and the update, and then I can do a wait, at which point I know that all 3 streams are finished, so I've got 6 buffers ready to go over the network. Well, actually, I can do a bit better than that. I don't have to wait for everyone to finish. What I could do is I could launch the 3 streams. When the X buffer is ready, send it to the network. When the Y buffer is ready, the X buffer might be done first, in which case it's ready to go while these are still doing their transfer. And then when the Y is ready, send that to the network. And when the Z is ready, send that to the network. Do I know that X will finish before Y, before Z? No, I can't guarantee that. It's likely because they were launched in that order, but there's no guarantee of that. But this is probably the best I could do. If you wanted to use the Cray, sorry, not the Cray, the OpenACC runtime API, you may be able to do something a bit more fancy. There's no wait any directive, but what you could do is have a loop that tests, has X finished, or Y finished, or Z finished? Oh, Y has finished. I'll send the Y buffer. So you could do that as a further optimization. It may not be quicker, because you spend so long kind of going through all this loop and doing all these tests. It might just be quicker to do these things. It's just, again, it's the sort of thing that you have to just test in your application. At that point, I could already have started launching the copy of the bulk back into P, and I'd do that and I'd just give it another handle, another stream. And then when I come down here, I've got a network barrier, at which point I know that those send buffers that I sent before have been received. So now I have separate streams to send the receive buffers to the GPU, and then little kernels that will unpack those buffers back into the main data array. And I launch one stream for X, one stream for Y, one stream for Z. I have an ACC wait here, so that's, at this point, I'm assured that the bulk copy is finished and each of the X, Y, and Z buffer unpacks are finished. And at that point, I can end my iteration loop or go back to do the next iteration. So obviously, I need extra buffers. I need 12 buffers, X, Y, Z, up and down, and I need that for send and receive. So these buffers will need to be added to the data regions, because I don't want to keep, I don't want to move them unnecessarily, and ideally, I'd like to try and create them once. So ideally, I'd like to go up to the main program and put them in the main data region, so I never need to worry about creating these. So I would say they're present in the Jacobi routine or create in the main data region. Here, it probably doesn't matter whether I say create in the data region just inside that Jacobi routine, or whether I go up a level and I say it's create in the main data region, and then just say it will be present when you get in the Jacobi routine. That's because it doesn't matter, because I only call Jacobi twice. If I called Jacobi every iteration I did that call, creating these buffers, allocating them on the GPU every time I call this routine does have a time overhead. So if you're calling a routine a lot, it's much better to have the temporary arrays being present in that routine as opposed to allocating them every time you hit it. So how could I actually do the message passing? I could use MPI, I could use coarrays. If you've not seen Fortran coarrays, you don't need to worry. It's a part of Fortran 2008. It's a part that Cray is quite fond of because in some circumstances, it can give you much better performance, and the Cray hardware is very suited to Fortran coarrays. But what I'm saying here doesn't rely on you knowing any of that. If you've not done MPI or coarrays, then this all may be a bit new. So with MPI, to get overlap, you can use non-blocking calls. So you have MPI I receive, and this is saying, I'm going to receive data into these buffers. You should put these receives as early as possible. First thing in the iteration loop, get the receive buffers posted. When you get each of these X, Y, and Z buffers up and down ready with these streams X, Y, Z, you'll then do an MPI I send, which will send those off. And you do that as each of these becomes ready. You've then got your network barrier. Well, the network barrier is an MPI wait all. I've got 12 buffers. Some are send buffers, some are receive buffers, so I'm going to have to wait for all 12 messages to complete. Because messages here means I sent something or I received something. So there's 6 things sent and 6 things to receive. So that's what you could do. You could say MPI wait all for these 12 messages. I know they've all received, and now I will unpack all these buffers. But if I'm doing it this way, when each buffer that is received has to be transferred to the GPU, it has to go across the PCI bus. Only one message can go across the PCI bus at a time. When I do the wait all, I'm suddenly going to try and send send 6 receive buffers across the PCI bus. What can sometimes be better is to use a feature called MPI wait any, where basically what I would do is I would say there's 6 buffers coming in. I don't know what order they're coming in. They're coming in from 6 different directions. I've no idea which will come in first. So what I do is I wait and see which of these arrives. And I'll know, it will tell me that one has arrived, and it will tell me which one has arrived, so I know which buffer it is that's come in. So at that stage, so basically I have a do loop that runs from 1 to 6, and within that I'll have a wait any, which will wait for the next message to come in. Depending on what the label is for that message, I'll then, if the label is 1, then it's the receive buffer in the X up direction. And so at that point, I will kick off 2 kernels, one after the other. Sorry, an update to the device and an unpack of that buffer on the device, and I'll give it, say, stream handle number 1. Immediately, that's all sent off to the GPU, right, copy that buffer, then unpack it. Immediately, I come back, and I go round the loop again, and I do the next MPI wait any and get the next buffer. So it doesn't matter what order these buffers are coming in. As soon as one comes in, I get it moving across the PCI bus, because here, the PCI bus is serializing everything that's going on. That's the big bottleneck. And of course, once all of these 6 are in, I do have to make sure that the send buffers are ready to be reused, so I'd have to wait all on the 6 messages. There's no point doing wait any on those, you just do a wait all on those 6 messages. Is this strategy faster than this one? It can be. But like all these things, for every argument that something is faster, there's always an argument how it might not be faster. So it's the best thing to do is to test the 2 strategies. Calculating GOSA, this global residual, is a collective operation. So far, I've been using blocking collectives. In MPI3, there are non-blocking collectives, so there may be more potential for overlap on that, but I've not investigated that. So if you're using Fortran coarrays, this is another way of passing messages. It's a more single-sided way in that I've got some data, I send it to you, but I'm not going to tell you that I'm sending it, and you've no way of knowing that I sent it. It will just arrive at some point. So that can have improvements, but it also means that you have to manage the code a bit better. So if I want to send a buffer from here to its neighbor, basically all I do is I say, in the receive buffer at the remote processor, you should receive the data that came from the local buffer here. Now, if you've not seen coarrays, I wouldn't worry. But we did get for the Himeno code, we get slightly better performance using the coarrays than we did with the MPI, but these things tend to vary as the MPI and the coarray libraries variously get improved. The one thing you do need to watch if you do use coarrays is that because you should be able to say, to set z equals x in Fortran, you can say y equals x and z equals y, and then z is equal to x. But that should also work if y was on a different processor, bizarrely. That should still be legal Fortran. So the fact that everything is supposed to just happen completely asynchronously and with no control, the compiler is forced to add a lot of synchronization points to make sure that this sort of thing doesn't end up as a race condition. If you want to get rid of these because you're very confident that your code will not have race conditions, then you have to add directives in with the Cray compiler. So it's a bit of a hack. So what you do is you send the buffers off just by saying, and over there you should receive a copy of my local send buffer in your receive buffer. How will you know it's arrived? Well, you have to do a synchronization. And similarly, you're going to have to take the local values of your residual, and you're going to have to combine these together. Now, a very technical point, if you are interested in using coarrays with OpenACC, currently, due to big worries about race conditions, you can't put a coarray into an OpenACC region. So you can't put it in a data region, you can't put it in a parallel loop. So if you want to use coarrays, you have to use ordinary variables inside the kernels and then copy them into a local part of the co-array. Now, of course, that does mean you're doing additional copies. So some of the improvements that you sort of see with co-arrays are not quite as great. So if you looked at what the co-array implementation looks like, the block diagram looks just like we were seeing before. The details have changed in exactly how you did that, putting the data across, and how you did the barrier. But as I said, it doesn't require a vast number of directives even to do the parallel code. And you have done it all in a way where the same code would execute on the CPU, albeit you would be doing buffer packing that you might not have done if you were working on the CPU. So I'm afraid the performance tests I've got for this are on an old system. So the newer XK7 with a better GPU, the GPU tends to go faster. But looking at the performance, the best performance we could get on the CPU was a hybrid MPI OpenMP, scaling very nicely out to 128 nodes. But the GPU versions, one version where we didn't use the async clause and one version where we did, are node for node faster. So again, OpenACC for parallel codes running on GPUs is not necessarily, people say, oh, well, it'll never scale or whatever. It's scaling pretty well. Of course, this line, there is curvature on this line, more than there is there. You are fighting against data transfers between CPU and GPU. You can overlap them as best you can, but the trouble with a strong scaling problem is, as the local volume gets smaller and smaller, the amount of time on compute gets smaller and smaller. Yes, so do the halo buffers get smaller, but when you send a halo buffer, there's a latency cost that never gets smaller. And after a while, the scaling is always going to suffer in strong scaling because there just isn't enough work to overlap. And of course, this very simple code has particularly little work. But then you profile the code and you look at how, as you go out on the number of nodes, of the 100% of obviously the execution time is reducing as you increase the number of nodes. But if you normalize it and say, yes, of its execution time, what proportion is spent in different operations, you can see that as you go out to more nodes, less and less time is being spent on the kernels, more and more time is being spent on buffer copies and network. And so by the time you get to 128 nodes, only about half of the time is actually in GPU compute. And so again, if you're trying to strong scale this problem, you need to think a lot more about opportunities to improve the communications rather than improving kernel efficiency, because it's no longer becoming the full limiting factor in your application. So far, what I've talked about there is assuming that MPI, your communications, are launched from the CPU, and that data must be on the CPU in order for it to move to a different node, in order for it then, from that CPU, to go to the GPU. Now, what is available from a number of different vendors, I mean, whether you're on InfiniBand and Cray is developing it on with their MPI, is that you could call MPI, but instead of giving MPI a buffer that's on CPU memory, you give an MPI the buffer that's on GPU memory. And so the data will move directly from the GPU to, well, wherever either a remote CPU or a remote GPU. But for what we're doing, you probably want it to go from this GPU to the neighbor GPU. And it does this in a much more, it doesn't do it exactly as you do it. So there are performance benefits in getting hardware performance benefits from doing it that way. But the other performance benefit that comes in is the fact that we spent a lot of time, if you go back to these pictures, we had to pack these buffers, and then we had to synchronize to make sure the buffer was ready. And then we had to, over here, we had to make sure we'd synchronize to know that the buffers had been received before we sent them there. So we've got extra GPU synchronization going on, as well as our MPI or co-array or whatever synchronization. So with the parallel code, there's these extra steps of synchronization. If you can call MPI directly, then all you need to do is pack the buffers on the GPU And then you launch MPI, and at that stage, you don't need to do any more synchronization other than completing the MPI, doing an MPI wait. Because at that stage, you know that not only the receive buffers arrived at the other node, they've not arrived on the CPU, you know they've arrived on the GPU. So regardless of the fact that they may have traveled a little bit faster, the big benefit is that you didn't need to, as the host, the CPU, you didn't need to have these extra synchronization points. And if that synchronization point means that your code has got to be ready to do that. So if you were trying to overlap, this is a very simple code, but if you've had other computation you could have been doing, you can't go and spend much time on that because you've got to come back and synchronize. Whereas here, you could have called a subroutine to go and do something completely different. And you've got quite a long time where you know that you could complete that computation while all of the MPI overlap is being done and the data is moving to the remote GPU. And the only synchronization that's going back in is your MPI wait, which is exactly the same synchronizations that you'd be doing for the CPU. So that's, from my perspective, the big advantage of being able to do GPU and sending data directly. And so it's coffee break now. After the coffee break, I will mention just briefly, again, how you would do that. So every parallel code is different. Every parallel code does it in a different way. There's no way to kind of answer all the questions, but I hope this kind of gives you some flavor about the sorts of things you can do and the places where there are quick wins to use overlap, even if you just worry, packing buffers and so on. Are there any questions on that? Has anyone ever done any parallel codes with OpenACC? One. And good scaling, bad scaling?
Well, okay, actually, I'm completely with you.
Oh, right, okay. A work in progress. Yeah. So there is, in the parallel code directory of the tutorials, there is an example of the multi-grid code. It's not very optimized, it doesn't use async too much. But there is an example in there of doing a parallel code with OpenACC. Because you're going to be playing with that as part of the CUDA tutorial and learning how to run a parallel code and how you can use the GPUs in different ways. But there is an example there. I think we have to have coffee now, otherwise it'll be lunchtime. Like what we saw before, there's an initmt that initialized the local matrices. It calls this Jacobi routine twice. The first time it was calling it just to calibrate what it did later on. And there was the second call where it actually did a performance estimate. But the new thing in there is that it also has to set up the processor grid because it decomposes this 3D problem into a 3D grid of processors and then splits the problem over those. So if you want to do this stencil update, obviously each local problem is going to have to share halos with its neighbors in order to calculate the full problem. And it's going to have to do that at each iteration. So the difference is when you look at the iteration loop that we saw before in the Jacobi routine, there's the loop over iterations. Obviously, that's a manage that you've got these two memory spaces, the CPU and the GPU, and you have to make sure that the data that you want to send is in the CPU memory in order to talk to the network. Now, there are some ways that you can get around this that are more advanced, and I'll talk about that a little bit later. But this talk is looking at the sort of extra things you need to consider. So I'm not going to talk particularly about tuning kernels or anything like that, because we've done all that. So what I'm going to talk about is, first of all, in a more conceptual level, what sort of things you're going to do and how do you do those in OpenACC. And then there are different ways, different communication models that you can use. You could use MPI, you could use Fortran coarrays, but I'll say a little bit about these two examples at the end there. But most of what I say is actually quite common to both of these calculations. So the code I'm going to talk about, because that's better. I mean, at the risk of giving the game away, a parallel code is just like a scalar code, but with data transfers. You don't ignore the scalar part of the code, and so what we've been talking about so far is scalar optimizations. So for a parallel code, you do go through the same exercise that you would do, that we did yesterday, looking at a scalar code and tuning the kernels. The other thing you need to consider is how data moves between CPU, between the different nodes, and the added complication when you're dealing with a hybrid system that has GPUs is that the GPU isn't talking directly to the network, at least in this sort of, when you start thinking about things. The GPU talks to the CPU talks to the network. So you have to, it makes, it's familiar with what we've done before, is this Himeno code, this Stencil code that we looked at yesterday running scalar. There's a parallel version, and so I'm going to talk about the parallel version because obviously the structure of the program looks very similar. So you've already seen a little bit about this. I'm talking about a strong scaling benchmark. So this is where you take a particular global problem size and you're going to split it up over more and more nodes. The code itself, I'm going to mainly talk about the Fortran version. It's about 600 lines of Fortran. To port this to the accelerator, we used about 25, 30 directives. So that's more than we were using for the scalar code because there is the extra complication of all these data transfers. So what does the code look like? Well, it's the machine room, and it's like a zoo. There's so many different systems to see there. I've never seen such a selection. It's brilliant. So today I was going to start with a brief look at what you do if you've got a parallel code. So for some people, this isn't really something that they're going to necessarily do. But if you're really going to use a system like a Cray XK7 or a big GPU cluster, one GPU will not do the entire job for you. You do need to have multiple nodes working together on the problem. So porting, this is the wrong presentation even, porting to such an application